let's take a look at more cosmology. And we'll start out with something called the cosmological principle. This is the idea that the universe is homogeneous and isotropic. Homogeneous means that the universe is the same everywhere in space. So one part of space is the same as another part of space. Now this, of course, ignores the lumpiness of the universe, that the universe has galaxies and clusters and stars and so on. But the average of the universe over large scales is about the same. Isotropic means that it looks the same in all directions from our perspective. And both of these ideas that make up the cosmological principle are upheld by observations. The more we observe about the universe, the more these two things seem to be true. Now we're going to consider what the shape of the universe might be. Now, based on general relativity, and we're not going to get into general relativity right now, but based on that, there are three possible shapes for the universe: closed, open, and flat. A closed universe would be of finite size, and we kind of visualize it in 3 dimensions as being spherical. It's also called positively curved. Now, the universe could also be open. An open universe is of infinite size, and it's sort of saddle-shaped, if we imagine it in 3 dimensions. It's negatively curved is another way to describe it. Or the universe could be flat. Flat is infinite, but also unbent, and we visualize it as kind of a plane, like that. So how would we know which shape of the universe is true? Well, if there's enough matter in the universe, turns out that gravity would be able to bend space itself into a closed shape. And if there were enough matter to bend it in this way, eventually the expansion of the universe would be reversed, and the universe would stop its expansion, and instead it would contract and result into a collapse, or something called the Big Crunch. Now, if there isn't enough matter in the universe, then gravity can't stop the expansion, and the expansion just keeps going forever. We get infinite expansion. That's an open universe. Now, if there's just enough matter, then gravity would be able to asymptotically slow the expansion until eventually, after an infinite amount of time passes, the expansion would stop, but there would not be enough matter to reverse the expansion. So, okay, what density is necessary to stop the expansion? We can look at this in terms of energy. So the total energy of the universe we can write as 1/2 mv squared plus negative gmm over r. In other words, the kinetic energy of the universe plus the gravitational potential energy of the universe. Now, the kinetic energy of the universe we can write this way. We can replace the v with Hubble's constant times r. R here representing the distance between things. So, okay, we put that in there. And then we can replace the mass of the universe with 4/3 pi r cubed, the volume of the spherical universe, times the density. Okay. Now, if there is a stalemate here between this kinetic energy associated with the expansion of the universe and the gravitational potential energy associated with the gravitational attraction of all the mass in the universe, if there's a stalemate between those two things, then the total energy would be equal to 0. And if that's true, then we can set 1/2 m Hubble constant squared r squared equal to 4/3 pi r squared density gm. Okay. Now, a couple things cancel out. The m cancels out here, the r squareds cancel out, and we get an expression for the density of the universe equal to 3 times the Hubble constant squared over 8 pi times the gravitational constant. This is called the critical density of the universe. If the density of the universe is greater than the critical density, then that means that gravity wins. Gravity would be able to reverse the expansion of the universe. We lived in a closed universe. The expansion would stop, reverse, and we'd end up with a big crunch. If the density of the universe is equal to the critical density, then we live in a flat universe where the expansion would be able to be stopped, but not reversed. And if the density of the universe is less than the critical density, then there's not enough matter in the universe to stop the expansion, and the expansion will go on forever. We can represent this in a graph if we do the cosmological scale factor versus time. So if we live in a closed universe, this is kind of the idea here. We'd have a period of expansion, and then the expansion would decrease. If we live in a flat universe, we'd have something like this, where it would approach a flat line at time equal to infinity. And then if it's an open universe, then we would have something like this, where the expansion would continue forever. So in order to determine what the ultimate fate of the universe is going to be, it's important to know the density of the universe. And that is surprisingly hard to figure out. And part of the reason for that is something called dark matter. The story of dark matter starts with spiral galaxies. If we just look at the visible stars in spiral galaxies, we can determine approximately how much mass is there, and then we can determine what the velocity of the stars should be as they rotate around in these spiral galaxies. But then we can also observe what the actual velocities of the stars are in these spiral galaxies by observing redshift and blueshift. So if we do that, this is what we find. The expected velocity as a function of radius in a spiral galaxy should be this. That's based on the stars that we're able to see. But if you actually observe what their speeds are, this is what you find. The stars orbiting in spiral galaxies are moving faster than they should based on what we see. So what this suggests is that there's more matter in spiral galaxies than we can see. Now that matter that we can't see, we call it dark matter. Now if that seems a little bit shaky, like maybe there's something wrong with your observations, well, there's other evidence for dark matter out there. For one thing, galaxies in clusters, they behave as though there is some unseen mass in the cluster that is causing gravitational influences but not visible. Also, light bends around galaxies as though those galaxies have more mass than we can see. And then if we look at some galaxies, there's hot gas surrounding the galaxy, and it's trapped in the galaxy. It should be able to escape the galaxy, but there's some unseen matter there that's causing a gravitational force and preventing that hot gas from escaping the galaxy. So there's a lot of evidence for dark matter. But what is it? What could it be? If we can't see it, do we have any idea what it might be? Well, there's kind of two popular options. One is things called MACHOs, which stands for Massive Compact Halo Objects. The halo part just refers to their location. The halo is kind of the outer part of a galaxy. Now, massive compact halo objects would be things like black holes, neutron stars, brown dwarfs, which are essentially like big Jupiters that aren't big enough to be stars yet. And the idea is that this unseen mass is contained in these relatively dark objects that are just around. Now, turns out that this is pretty unlikely. If we observe these objects, or the ones that we can observe, there's not enough of them, or there doesn't seem to be enough of them to account for the dark matter out in the universe. The other option is something called WIMPs, weakly interacting massive particles. And these are subatomic particles that just don't interact with normal matter, except they exert a gravitational force. Now, there are proposals for what these particles might be, but by their very nature, they wouldn't interact with normal matter, and so they're very difficult to detect. This is an active area of research, and people are still trying to figure it out. Now, the other thing is dark energy. And the story behind dark energy is if we observe type 1a supernovae, they seem to indicate that the expansion of the universe is accelerating. Now, that's pretty strange. The universe really shouldn't be accelerating. If anything, based on what we talked about earlier in this video, the expansion of the universe should be slowing down due to gravitational attraction between all the matter in the universe. So we don't know what could be causing this acceleration of the expansion. We don't know. And so this unknown cause is just labeled dark energy. Now, it could just be a property of space. So as more space is there as the universe expands, there's more of this mysterious dark energy. Or it could suggest that we need a modification to our understanding of cosmology, but we don't know what that modification should be. So this is a very active area of research. Stay tuned. The last thing we're going to look at is anisotropies in the cosmic microwave background. And an anisotropy is a variation in the cosmic microwave background. So isotropy means it's the same in all directions. Anisotropy means there's slight differences. So it turns out that if you look at the cosmic microwave background very closely, there are hot and cold spots in it. And the idea is that after the Big Bang, right after the Big Bang, like within the first 10 to the minus 30 seconds, there was a period of very, very fast expansion. And this is called cosmic inflation. And during the period of cosmic inflation, which again was in the very first tiny fraction of a second after the universe was started, the universe expanded by an enormous factor, by a factor greater than 10 to the 20. So what that means is that previously very tiny fluctuations in the universe, like fluctuations on the quantum level, suddenly expanded and became absolutely enormous. So these fluctuations on the quantum scale grew to a size that was large enough to influence things on galactic scales. And these fluctuations in the universe eventually led to denser regions and less dense regions. And the denser regions eventually formed galaxies and galactic clusters.